Hey, I'm Rishit and I'm joined by Shivay in Spirit. So, there are a lot of things that you can do with physics simulators, like simulate fluids, or rigid objects, or deformables, or robots, or audio, or electromagnetism, and so much more. Many of these techniques, like Newton, warp, Tai Chi, and others, uh, often use different methods for differential simulators. However, we'll talk about building differential simulators in Torch and find a way to use AutoGrad so we can easily use this for training neural networks. Often, different use cases for simulation require different parameterizations and techniques to solve them. Differentiating through simulation sounds quite general, and a lot of things do transfer well. But let's focus on deformable and rigid bodies, simulated with the gold standard FEM with an implicit solver. And yes, we won't do any math today. This is all the mathy stuff that you'll see for today. We can view this as starting with the position and velocities. From this, we do something and get new x and v's, and so on and on. And this makes a simulation. Simulations can be run with multiple parameters, producing multiple different simulations. How do we, for instance, know which one of these three simulations is true compared to a real video? Or how do we make simulations produce things we want, like in the spheres and for many other tasks? How do we make it do what we want? One way could be to run many such simulations every single time for every task, for every scene, and then find some way to choose a simulation from the grid of simulations. This, of course, has multiple problems and can't be used reliably for some tasks. Instead, let us take this and add some params, like those from a neural network on the left and some loss function on the output of the simulation. Great, let's train this network by running it through AutoGrad. And that's the end. Or I actually wish it was. I wish that was the end. But AutoGrad has some assumptions baked into it, which are usually not a lot, but many of them are violated here. So if we need to find a way to make it work for both each simulation step and across all the simulation steps you have. And yes, we'll often use things that we know from ML. So let's first go. The assumption that all of our ops are smooth and differentiable is not directly broken by collision handling. If you use the popularly used IPC with continuous collision detection, because you have log barrier potentials which are differentiable. We assume CCDs, so two objects don't intersect, which could cause a problem. However, this log barrier causes gradients to get very high when d is approximately 0 or the distance is approximately 0. So from what we know from ML, early during training, we can instead use a smooth L1 in place of log barrier. The Coulomb friction model, on the other hand, violates this assumption. The subgradient is not defined as well due to the slip or stick binary condition in the Coulomb friction model. Again, we can replace this entirely with a smooth approximation of the friction model. So we never model these two individual slip and stick parameters. If you use a co-rotated FEM model, we haven't talked about all material models yet, but for this popular model, you can use a stable Neo-Hookean material, and we can clamp the Jacobians. So when the Jacobian tends to 0 plus, the smooth clamped quadratic volumetric strain energy stays bonded, like we see in these plots for simulations. The orange curve stays bonded when you clamp Jacobians as they tend to 0 plus. Let us see what does this arrow contain. This arrow has some number of Newton iterations with conjugate gradient, and it uses line search, which changes the effective map we have. The gradients depend on the iteration count and the tolerance we use. Boundary conditions are also clamped after the solve or post projection, which hides all of the true dependencies that this has. In an implicit step, the next step is defined by an equation like backward Euler, like we see on that arrow, or even contact KKT with IPC log barriers. If you enroll the Newton or conjugate gradient, AutoGrad learns the loop which depends on step count, line search choices, and tolerance. Instead, we can use implicit differentiation, which uses the equilibrium. At the solution, we are in equilibrium, so we can instead solve one adjoint system, one transpose solve, and reuse the same matrix and preconditioners as we did in forward. In turn, we do get less accurate. Gradients, and we need the final states to be in equilibrium. But for the adjoint, we never build the Jacobians or the Hessians. We only need the products with them. In each CG step, we apply the stiffness vector product using what we get from computing the residuals or energies. This makes the backward memory light and fast because the cost is only a handful of matrix per conjugate gradient iteration. And we reuse the forward preconditioner. So adjoint iterations also mirror the number of forward, also mirror the counts that we had for forward. Further, for making locally stable computational graphs, we should use what we did for contact, friction, and for implicit differentiation, which makes this assumption satisfy for line search and early stopping. Further, we should not perform post-clamping conditionally. Instead, encode the boundary conditions, like the red dots over here, inside the linear system itself. To make Jacobians reasonably well-conditioned, we should reuse what we do for applying boundary conditions. Further, make sure your time steps and number of forward substeps are correctly set. Now, in most cases, when you don't care about differentiability, you can usually see the effect of setting time steps visually, like the one on the left. But when differentiating through simulations, don't just see these visual results, but also see the condition number for Jacobians. I do want to say that differentiating through a simulator is a hard problem. In many cases, you'll still get not so great gradients. This is much like the problem we see in differentiable rendering. We can do a bunch of tricks, but it is possible that the gradients just might be completely wrong because the overall process is not really smooth. We can have one big change for close-by inputs. Remember that the backward pass needs access to everything that happened in the forward pass. We need to stir everything that happened in the forward pass somehow, so when we are doing backward, we can get back to it in autodef. But then it becomes really hard to store everything across simulation steps because we have, let's say, a bunch of simulation steps, each of which has many substeps, and we somehow need to store all of it. So we can, again, borrow things from ML. We can checkpoint across this number of solves we do. So we can perform gradient checkpointing for every case steps in the simulation instead. Another assumption baked in AutoGrad is that the backward pass should match the converged forward pass. You might think we can use something like VQVAEs, which have the same problem. The forward pass uses the vector quantization, which is not differentiable. So the forward pass and backward pass become different. It turns out we cannot use what VQVAE did, which was gradient skip through the quantization. It works in VQVAE because the decoder sees a stable piecewise constant latent, and STE provides the useful learning signal. And then the commitment or codebook losses and EMA stabilize codes and reduce mismatch. Here we can converge the forward solve tightly by fixing the absolute or relative tolerances and stop only when the fixed point residual is small. Then use the exact tangent from forward in backward. So reuse the same assembled Jacobian or Hessian and preconditioner. We should stop grad through the line search, trust region, warm starts, which are for convergence only. So compute gradients at the converged values, not through the path. When contact happens, the barrier stiffness and activation distance look something like this ball. And the contact set points also change. So we can freeze the contact set per inner solve by building candidates with CCD and then keep that set fixed during the Newton solve and only update between solves. We can also freeze the barrier parameters within a solve and keep the barrier parameters constant for the inner solve. This allows us to use continuation or change these values, in which case we can treat each stage as separate forward solve and differentiate only through the final stage. Finally, we can assemble all the barrier terms into the same energy or tangent used by the solver. Also, a shameless plug to Torch DiffSim, which was used to make all the demos I showed earlier and implements everything I talked about today. Torch DiffSim allows easily doing FEM simulations and differentiating through the simulator. Mainly, it is very minimal and can be easily integrated in training your neural networks. Now, I've gone through a bunch of things very quickly, but I encourage you to try these things out with Torch DiffSim.